Professor, we can start. We are now transmitting online.
Okay.
Okay, I will introduce you, okay? Um, well, welcome to everyone, and thank you for joining us today. It's my pleasure to introduce our distinguished speaker, Dr. Ramon Lopez. Dr. Lopez is a renowned space physics and professor at the University of Texas at Arlington with a PhD from Rice University. He has made significant contributions to our understanding of solar wind magnetosphere coupling, space physics, and science education. His leadership in national academies, commits, and NASA advisory groups, along with prestigious awards like the APS Nicholson Medal and the APS Edward Botch Award, highlights his impact in the field. A dedicated advocate for diversity in science, Dr. Lopez continues to inspire the next generation of researchers and educators. Today, he will share his insights on solar wind magnetosphere coupling, a crucial topic for understanding space weather and its effects on Earth. And we are honored to have him with us. And please leave your questions in the Zoom chat or on YouTube comments, and we will address them at the end of the talk. Also, the comment can be in Spanish and Portuguese. And we would like to say thank you to Professor for your time today. And now, Dr. Lopez, the floor is yours.
Okay, thank you very much. And yeah, questions can be in English, pueden ser en español y también puede ser en portugués. But I'm going to give you a brief overview of solar wind magnetosphere coupling because I could spend, hours actually talking about this particular topic. And so here's sort of the outline. I'm going to talk about magnetospheric convection and the polar cap potential, geoeffective length, force balance in the magnetosheath and deflection of the solar wind flow, and two particular cases. I'll talk about viscous interaction for northward IMF, and then some conclusions. So we really do need to begin with some basics just to make sure everybody's on the same page for some of the things that I'll be talking about. For particles in motion in electric and magnetic fields, so they're moving in response to this total force, which is the Lorentz force, and there should be a vector over the B here because that's a vector, and then the electric force. And now, if there's no electric field, if there's only a magnetic field, then this is easily solved, and the particle just moves in a circle around the around a central point, which we identify often as a magnetic field line. Although magnetic field lines are not real, you should know this, they're useful in thinking about the systems and the physics, but there are limitations because there is no such thing as a magnetic field line per se. But now, just the QV cross B motion is simple, but if we add electric field, now it becomes kind of complicated. So let's see if we can make it simple by assuming that the velocity can be broken up into two components, some drift velocity and then that gyro motion, which is just coming from the QV cross B. And when we do that, we get that the particles drift with this E cross B over B squared. That's the electric drift. And here you can see physically how that happens. So here's my magnetic field. And if there were no electric field, the particle would just go in a circle. But with that electric field now, okay, the ion comes, it's moving against the electric field, it's losing energy, gets turned around, and now it accelerates, going to higher speeds as it gains energy moving along the electric field. And so at this point, the energy is greater, the velocity is greater, and the size of the loop that it makes around the magnetic field is also greater. But then the process repeats itself, and you can see that the center of motion is drifting from left to right. Now, electrons, much lighter, much smaller mass, so their motion is faster and smaller circles, and they have opposite charge, but actually it doesn't matter. We get the same effect, that the electron moves in the direction of the electric field, and that's taking energy away. So tighter circle, and now it moves opposite to the electric field. It's gaining energy, and bigger circle, and we get the same thing. And the electrons drift in the same direction with the same drift. Now, in the frame of the particle, if we move into this drifting frame, all we would see is that the ions and electrons are gyrating around the magnetic field. What we've done with this coordinate transformation, or this velocity transformation, is to essentially remove the electric field. So in the frame of the particle motion, there is no electric field. And whatever electric field is there, or which is consistent with the motion, depends on the bulk plasma flow, and it's relative to an observer. So if you're an observer and you see ions and electrons drifting, that means there must be an electric field, and it has the magnitude that would give you this electric drift. But if you move with the plasma, if the plasma is drifting with some drift velocity and you move with it, you see no electric field, and you just see the ions and the electrons gyrating around. And so this is very, very important, that electric fields are completely dependent on the frame of reference. And so you hear sometimes people say, well, the electric field causes E cross B drift. No, that's not true in space plasmas. Plasmas will move, and if you see the plasma drifting, there has to be an electric field that's consistent with that drift, because, of course, you could drift with plasma and there would be no electric field. And in general, there's something called the BV perspective. And in the laboratory, in your home, you turn on a switch and a current starts to flow and goes to operate whatever device you've got. And there's a magnetic field that's produced by that current, consistent with Ampere's law. But in space plasmas, because of the scale size of the system, you have to ask, well, which can adjust first, the magnetic field or the current? Remember, the currents in space plasmas are motions of particles, but the motions of those particles are affected by the forces on the particles, the magnetic forces, for instance, or electric forces. And so in your home, yes, when you turn on the switch, because of the scales in the system, the current flows and makes a magnetic field. But in space plasmas, we have a different way of thinking about it. Instead of thinking about electric fields and currents, which is what you think about in your house when you turn on a light switch, we're thinking about, well, what about the magnetic field and the flow of the plasma? So plasmas will move, and they will move in response to the net force that is applied to the plasma. And in whatever frame of reference you are in, the electric field that you see is what is needed for that E cross B drift to account for the flow. So that would be the self-consistent electric field. Now, as the plasmas move, they're dragging the magnetic field with them, because the plasma is essentially infinitely conducting. And so the magnetic field remains fixed to the plasma. So if I drag if the plasma moves, then the magnetic field has got to be fixed to the plasma and moves with it. Now that's going to create magnetic shear. It's going to create some kind of magnetic field that's dependent on position. And the curl of the magnetic field is what gives you the current, and that's Ampere's law. So in space plasmas, forces act on plasmas. The plasmas move. The electric field that you see in your frame of reference is what is consistent with the E cross B drift. And then as the plasmas move, they drag the magnetic field, and the current has nothing to do with an electric field and a conductivity in the plasma. The current is given by the curl of the magnetic field, Ampere's law. So how does the solar wind actually transfer momentum and energy to the magnetosphere? Well, the solar wind is flowing past the magnetosphere. It's here coming from the sun and flowing past it. So all of the momentum in the solar wind is aligned with the direction from the sun to the earth. But we want to transfer that momentum across this boundary. And so it is a transverse transfer of momentum across the magnetospheric boundary. And there are two mechanisms by which this happens. And they were both proposed in the same year. Jim Dungy proposed reconnection, which turns out for Earth, not necessarily for other planets, but for Earth, that's the most important part of the interaction. So here is a diagram illustrating that Earth's magnetic field on the day side points north. And if the magnetic field in the solar wind, the interplanetary magnetic field, points south, then you can have merging on the day side. Now, merging is where that frozen influx condition breaks down, and particles lose the identity of a particular field line, which is not a real thing anyway, but they lose that identity and magnetic topologies can change. And so that's what happens here. And now we have a magnetic field line that's connected to Earth on one end and to the solar wind on the other. And you can see that there's this big bend right here, which means that there's a big tension force pointing out from the bend. So that is pulling all of this out, and the solar wind is flowing down this direction. So the solar wind flows and it drags the magnetic field, which is now connected to the ionosphere with it. When it does that, it's transmitting a force to the ionosphere. And that force, it's in the form of an Alfvén wave. You can think of it that way because here's a bent magnetic field line, and this kink is going to propagate down into the ionosphere. So you can think of it as an Alfvén wave, but Alfvén waves also have a current in the direction of the magnetic field. Remember, an Alfvén wave, the perturbation from the magnetic field is perpendicular to the background. And that means that there's a current which is perpendicular to delta B, which is along the main magnetic field B. So an Alfvén wave is also a current that flows along the field line. But Alfvén waves have an electric field and a magnetic field to them, and so they carry pointing flux. Because remember, all electromagnetic energy is transmitted by pointing flux. And so that pointing flux goes down along the field into the ionosphere as well. So you can think of it as a force being transmitted to the ionosphere. You can think of it as an Alfvén wave going down to the ionosphere. You can think of it as pointing flux going down to the ionosphere. It's all the same thing. But that sets ionospheric plasma in motion, as we will see. Now, when the field gets dragged into the magnetotail, it eventually gets pulled into a distant reconnection region, and the field reconnects and snaps back to Earth, this dipolar part, and then this part becomes disconnected, continues to flow down stream from the solar wind. That's the basics of the Dungy cycle reconnection for southward IMF. Now, Axford and Hines had a different idea. They thought that, well, maybe there could be some kind of viscosity. You know, if you take your take a cup of coffee, and you take your spoon and just move it around the very edge of the cup of coffee. You're not touching the coffee in the middle of the cup, but soon the coffee in the middle of the cup will start to rotate around as well. And that's because as the coffee starts to move, next to it is a bit of coffee that's not moving, and that drags on the coffee that is moving, and it gets pulled and starts to
Pregunto porque a
move.
veces no sé si las haces como con intención de que me vaya o que yo te diga.
Who's talking? Somebody was talking. So mute yourself unless you have a question, okay? But if you have a question, you can go ahead and ask it. But if you don't have a question, mute yourself. So as the solar wind flows around the magnetosphere, inside the magnetosphere, plasma starts to get dragged. So that's an example of momentum in this direction being transmitted perpendicular to the direction of the momentum. That's what we call transverse transport of the tangential stress, because the stress, the momentum, is tangential to the boundary, and it's got to be transmitted across the boundary. So the plasma flows and then has to at some point turn around and come back, and you get this circulation. And this is called the viscous interaction, which is generally only about 10 to 15% of the total interaction, but at Earth and under the right circumstances, it could be much bigger because it depends on the speed and the density of the solar wind. Actually, for the outer planets like Jupiter and Saturn and the other gas giants, the viscous interaction is actually more important than magnetic reconnection in terms of transferring solar wind energy to those magnetospheres. And here's a diagram of the viscous interaction, or actually a model simulation result. This is looking down on the magnetosphere. This is the equatorial plane, and these black arrows are the velocity vectors. And you can see here's the solar wind flow. It hits the bow shock, it gets deflected, and it's flowing around the magnetosphere. But here at the boundary, you get these swirling regions of plasma because the plasma is slowly being dragged by this flow, and then it causes this kind of circulation. And here we have a magnetic field line. You can see that that's getting all wrapped up. And that also means that there are currents that are flowing here. And those currents are flowing in the same direction as the currents for southward IMF from reconnection. So those currents are flowing in on the dawn side of the Earth into the ionosphere and out on the dusk side. And that's the viscous potential, that this solar wind flow drags the plasma, and then the plasma comes back. Now, because the plasma is being dragged one direction and the other direction, the magnetic field is being dragged in those directions as well. And that means that there's a change in this direction, in the Y direction of the field that's in the X direction. And that generates a current. And that circulation is being transmitted down to the ionosphere, where it produces a force that sets the plasma in motion to have exactly the same kind of circulation. Away from the Earth, so from day side to night side at high latitudes, and then closer to the Earth at lower latitudes, there's the return flow. Now, reconnection is a fundamental process, and magnetic field lines connect and convert magnetic energy into plasma energy. In fact, if you didn't have magnetic reconnection, then all, say, the energy in stars would be tied up in the magnetic field, because the convection of the plasma in stars like our sun, that twists up the magnetic field and stores energy in those magnetic configurations. If that energy could not be released, if there was no reconnection, then stars would eventually freeze, because all of the plasma motion would be stored in magnetic field. But that's not what happens, because when you get to very large currents or very small scales or various other mechanisms that people talk about, then that frozen influx condition where the magnetic field is tied to the plasma breaks down, and then the plasma and the magnetic field can decouple, and that's when you have reconnection. But here's a diagram of that reconnection region. Again, a simulation. This black is the inner, this is the inner edge of the MHD simulation, and then everything is propagated down into the ionosphere where another simulation solves. But in this black region, there's no simulation. It's just projecting along dipole field. So here again for southward IMF, and also with the viscous interaction, we have this kind of system where the currents flow in on the dawn side. They'll flow across the polar cap and out on the dusk side. That means that there is an electric field, again, in the frame of reference of the Earth. And that electric field causes these currents to flow and is responsible for the plasma flow in the ionosphere. So both viscous interaction and reconnection drag the plasma at high latitudes from the dawn side to the dusk side. The Hall current flows in the opposite direction. And then the plasma circulates back towards the day side at lower latitudes. Now, there's another set of currents called region 2 currents, and those connect actually to the inner magnetosphere and are driven by pressure gradients. I'm really not going to talk about that. The higher latitude field line currents are the ones that are driven by the solar wind. But that driving by the solar wind causes all the plasma to flow in the magnetosphere, and that's what builds up pressure in the inner magnetosphere, which then is the source of the region 2 currents. Now, for northward IMF, we still have magnetic merging, but it's a rather different cycle. The merging occurs at very high latitudes. So the red lines are dipole and the white lines are open field lines. So, and the black are solar wind. So you can imagine the solar wind field line comes along here, and then it connects poleward of the cusp. This is the magnetic cusp in here. But here, the field is pointing out in the south, so pointing that way, and in on the north. And so that is opposite to the northward directed field. And so you can get reconnection here and here. But if I reconnect, then what I see, this field line comes around here. It was connected up here. So that's where the merging occurred, is here. But then that leaves a field line that gets dragged all the way around this way. And the solar wind is pulling in that direction. And that pulls the plasma actually towards the sun in this southern hemisphere. And the same thing happens in the northern hemisphere. So you get a reverse kind of cycle. And the reconnection occurs on the day side, because you can see this field line is about to reconnect with this one, and it'll produce a new closed field line and then a totally open field line. But you'll trap plasma on the day side. There's no flow on the night side at all due to northward IMF. All of the action takes place on the day side. Now we can see this if we look at spacecraft observations. So here's southward IMF, and this is DMSP F13, which is at 800 kilometers altitude, and it's flying this way. And what is plotted here is the flow perpendicular to the spacecraft motion. And so that flow is an E cross B flow. It has to be, because the plasma is in motion in my reference frame. And if that's V cross B, and B is pointing, this is in the northern hemisphere, so the field is going into the northern hemisphere, and that means that the electric field is pointing along this direction. So I can just, at each of these points, calculate the electric field and integrate, and then I get the total potential. across the polar cap. And what you see here is that there's this big region. This is fairly strong north-south IMF. Big region where the flow is all going from the day to the night. So that's connected to magnetic field that's being dragged downstream by the solar wind flow down the tail. And then there's the return flow here. And you see it in both hemispheres, north and south. Now here's northward IMF. And we see a very different situation. At the very high latitudes, there's this small region of the flow that's being pulled towards the sun. Now, it's small because the geometry is such that the reconnection region is much smaller. And that's why the energy transferred is much less. And it's also a very different kind of flow that's being set up in the ionosphere, because you have this flow towards the sun and then the return flow at lower latitudes. But then you see this other flow that's going back towards the sun. That's the viscous interaction. So viscous interaction is still there. But what happens for northward IMF is the viscous interaction gets weakened. And that's because of the flows that are being generated in the boundary layers. And I'm not going to go into more detail than that. There are papers that our group has published on this. But for northward IMF, the viscous interaction is weaker and reconnection itself is weaker. So there's much less energy transfer. Now, the actual reconnection rate, if I look at the size of these flows, it's the same, which means the electric field in here is about the same as the electric field here. So it's not that the reconnection rate is different for northward IMF, or that reconnection somehow is weaker for northward IMF. No, that's not it at all. The issue is that reconnection is much more limited. This is the only bit of reconnection that we have going on here. But for southward IMF, we get this whole big region where we have reconnection. And so a lot more energy is being transferred during southward IMF than northward IMF. So southward IMF leads this two-cell convection, and northward IMF leads to what we call the four-cell convection, the high latitude towards the sun and away from the sun, and then another lower latitude away and towards. But for southward IMF, they just add up because both cells are in the same direction. And we can get an estimate of the potential because, again, we can, these flows, we can say, well, that's the electric field along the path. So at each point, I just add up the electric field and I integrate and I get the total potential. And from peak to peak, that's what we call the transpolar potential. In this case, about 150 kilovolts of voltage across the polar cap. And that's a measure of solar wind magnetosphere coupling. Now, one of the issues with convection is that there's a basic problem that if I move plasma from the tail towards the Earth, as I have, in this picture, right? If these field lines start coming back towards the Earth, then the plasma in those flux tubes is going to be compressed because the volume of the flux tube gets smaller. There's something called the flux tube volume, which is the integral of ds over b along the field line. And this has units of volume per unit magnetic flux, because remember, B is flux times area. So, or flux per unit area. So, no, B flux is B per unit area, or B times the area, the total flux magnetic field times the area. And so if I put in the flux here, then the area would go up here and I get a volume of the tube divided by the magnetic flux. So this is the flux per unit volume. But if there's no energy going in or out of the flux tube, and there's not enough time actually for energy to go in and out, it's basically adiabatic convection, which means that PV to the gamma is a constant, and V here is that volume that's confining the plasma. So as I get closer to Earth, this gets very, very large and the volume gets very, very small. but this has got to be a constant. So if this gets super small and gamma is 5/3, then P has got to get very, very large. And so the pressures soon are unrealistic, unphysical. So something has to happen. And that's what storms and substorms and reconnection in the tail give you, is that if I start loading up the magnetosphere with southward IMF and causing this flow, then eventually the system is going to break. There's going to have to be reconnection in the magnetotail to get rid of this extra PV to the gamma, what is called specific entropy. And a substorm is when that energy is stored and suddenly released. And storms occur when you keep it up, when you keep on pumping southward IMF into the magnetosphere. Then you get a magnetic storm. And all magnetic storms then begin with a substorm. And sometimes people talk about storm times substorms, which may or may not really be substorms, but they're changes in the amount of energy that's being dissipated. But this only happens when you have flow coming up the magnetotail to produce this pressure balance and consistency. So you never get a storm or a substorm for northward IMF, and you will never get it for IMF BY either, even though IMF BY produces reconnection on the day side, it produces flow in the magnetotail, but the flow in the magnetotail is across the tail, not towards the earth. So you don't have this pressure balance and consistency. Storms and substorms only result from southward IMF. Now, how can we figure out what is the total amount of coupling if it's somehow related to this potential, the voltage that's put across the ionosphere by the solar wind? Well, the simplest thing is to say, well, I've got an electric field out in the solar wind, and so I'm going to have an electric field in the magnetosheath. This is for southward IMF, and it's going to be projected along this reconnection line into the ionosphere. So the polar cap potential should be the integral of this electric field integrated along the reconnection line. And so it should be proportional to VB south. And so should the potential times some length. This idea that the solar wind electric field determines the coupling in the ionospheric potential is called the Axford conjecture. And it's not quite right. It can't be, because actually the solar wind electric field is not the same electric field in the magnetosheath, because this is the electric field associated with this velocity, the solar wind velocity. In the magnetosheath, the plasma has a different velocity. It's slow because it crossed the bow shock. And so now the flow is subalphanic, submagnetosonic. And so that slow flow is going to have a smaller electric field. So the electric potential, the transpolar potential, is not directly controlled. It cannot be directly controlled by the solar wind electric field, but as we'll see, it is related to solar wind conditions. Now, actually, for low values of the IMF, the potential does respond linearly, as you might expect from this simple model, just LV/BZ. But for large values of the IMF, potential stops changing and just sort of becomes flat. And this is called saturation. And so how to understand that saturation? Well, to do that, we have to go back to some of this basic physics of, okay, if I've got some length in the solar wind that has got a certain voltage on it, I want to project that voltage into the ionosphere, then how do I think about that? Well, I have a length which we call the geoeffective length. And there's a voltage drop across that because there's an electric field pointing from dawn to dusk for southward IMF. Only the part of the solar wind that actually touches the magnetopause will transmit voltage. Because out here, the solar wind just flows past, and so whatever the solar wind electric field is in here, it doesn't connect to the magnetopause at all. And we've known for a very long time. I mean, what is that, more than this, 52 years ago? That what David Stern's paper in 1973, oops, you know, there's 32 RE from one side to the other. So if you just projected that straight out in the solar wind, that would be way, way too big. So the actual geoeffective length has got to be less. And it turns out that it's just a few RE, few Earth radii. Now, let's take a bit more sophisticated view of this. Let's say that this reconnection potential, yeah, it could be related to the solar wind velocity and magnetic field, but maybe there's a role for density. Maybe there's a role for the ionosphere, the Peterson conductance, or maybe internal currents like DST. But whatever this potential is, it has to be identically the rate at which flux crosses the merging line. That's Ampere's law. So imagine a block of solar wind coming with some velocity v, and let's just say in this block, the magnetic field is uniform and southward. And it's got a width L, that's geoeffective length, and some distance x in the x direction. So the flux inside this box, well, that's just the area times the magnetic field. So that's L times x times b. Good. Well, the rate at which flux is crossing the merging line is d phi dt. And so L and B are constants, so it's just L times dx dt, or V times B. So this is the rate at which the flux is crossing the merging line. But that raises the question of what is L and how is it established? And actually, under these circumstances, what happens in the magnetosheath doesn't necessarily matter, because this is the amount of flux. We're saying that this distance L, everything in here actually touches the magnetopause. And so that should be the time rate of change, which gives us the potential in the ionosphere. But how is this L established? Well, there were early studies that said it was about 6 RE. Remember that the full size of the magnetosphere is 32, but most of the flow goes around. So most of the energy in the solar wind goes around. And the energy in the solar wind is not in the magnetic field. No, no. The energy in the solar wind is all in the plasma flow, because the ratio of kinetic energy to magnetic energy is the alphane Mach number squared. The Mach number is V alphane divided by, or V solar wind divided by V alphane. And when you put in what the alphane speed is, and then you'll see, yeah, this is the ratio actually of the square roots of the energies. So the energy actually is the square of the Mach number. So if the Mach number is, say, 8, which is very typical for the alphanic Mach number in the solar wind, that means that the kinetic energy of the flow is 64 times as much energy per unit volume as the magnetic energy per unit volume. So the energy in the solar wind is not in the magnetic field, it's in the flow, the kinetic energy. So Pat Reif and Janet Luhmann got 6.4 RE, but they also noticed that for the largest values of B, this seemed to overpredict the potential. So it was hinting at saturation, but they didn't go there with that. But other studies show that, okay, the potential has no dependence on Bx, no dependence on By. For Bz, it's a very nice dependence for southward Bz. Very little on density, somewhat on velocity. And then Kp, that's an indicator of coupling. So this is, shows you that the magnetic activity in the magnetosphere is related to the potential. But again, the Burke paper, they got about the same kind of numbers, 4.5 or so. But for their highest bin, the average in their biggest magnetic field bin was 10.4 nanotesla. They got a much smaller geoeffective length. And they also had this phi naught is the viscous interaction. That's the intercept. If I plot the potential as a function of the solar wind electric field, when the solar wind electric field goes to zero, I still don't have a zero potential. That's the viscous interaction that I talked about that you can see is between 20 and 30 kilovolts. Whereas the potential coming from reconnection is more like 80, 100, 150 during storms. So you can see that reconnection is much more important in terms of that potential. So it was actually a few years later that Chris Russell showed this thing called saturation. But he also said, well, the ring current doesn't saturate. That's very strange because the ring current is supposed to be driven by convection. Well, I explained how that happens in a paper in 2009. But you see the saturation effect in anything you look at. Ionospheric plasma flows from superdarn to DMSP data, PC index, whatever. And it's in all of the MHD codes. So if MHD codes show saturation, it must be an MHD kind of effect. It cannot depend on microphysics because MHD codes don't have microphysics. And here is the potential as a function of southward IMF from the Lyon-Fetter-Mulberry code. And you can see down here, it's linear. The intercept gives us our viscous potential. We get a geoeffective length of 6.2 RE, which just comes from the slope. And when we get to large values of the IMF, it saturates. So MHD codes give you everything that you see in nature. So all of the physics must be in MHD. So there were various ideas about maybe that the weakening of dayside field by the region 1 currents would change where force balance was occurring, but that didn't explain things like saturation for northward IMF. And the idea of Alfvén wings forming for low Mach numbers, well, that only really happens for subsonic, but you still have saturation for supersonic flow. And Borowski thought that, well, only the Alfvén wing argument seemed to make sense, but no, actually it doesn't. That was shown by other papers that no, it's not correct. It cannot explain it. So we have to come back to what controls the geoeffective length, projection of the solar wind on the X line. Well, it's the forces on the flow, because that length L is what part of the solar wind is actually able to reach the magnetopause boundary, and that depends on the flows. So here is MHD equation, and I've taken a steady state, and so this is essentially the diversion of the flow, and this scale, this gradient scales like 1 over L. And that's equal to the forces acting on the flow. And so, yeah, the forces push the flow away, and we can see that all here. We can follow streamlines in simulations, or there's this cartoon. Yeah, so most of the flow goes around, and some part of it actually connects, transmitting the energy and causing the ionospheric potential to be what it is. Well, if we calculate the potential in the code and then calculate it by looking at the actual streamlines, they line up. So it really is this picture of whatever this width in the solar wind is, that's what gives you the potential. And that's shown by the fact that these lines lie on top of each other. So let's consider two limiting cases of the flow being controlled in the magnetosheath. Well, case one is plasma dominated and case two is magnetically dominated. So in the case that plasma pressure dominates, then the magnetic term, the J cross B term, goes away, and then this is what we're left with. But you see that it depends on the solar wind temperature, or not the solar wind temperature, but magnetosheath temperature, which actually depends on the kinetic energy of the solar wind. So this is going like V squared, and so those things kind of cancel out. And the rhos, even though this is the gradient of the density, if I double the density, I'm going to double the gradient of the density. And so that, so the only thing that would change if I increase the density is that the magnetosphere would shrink a little bit. That's just the pressure balance, the Chapman-Farrar scaling. But I can change the magnetic field and nothing happens. And so if the flow doesn't change, but I have double the magnetic field, then I'm going to have double the potential, because I'm going to have double flux crossing the merging line. Oops. Okay, now in the case where magnetic force dominates, we get rid of the plasma pressure term. And as the IMF increases, then, well, J cross B will increase and it will divert more and more flow. So eventually, as I increase the magnetic field, when this term is dominating, I also increase the diversion. So the amount of flux that actually reaches the boundary doesn't change. And that's saturation. But if I increase the density, then this whole term gets smaller and there's less diversion and the potential will go up. And we can see that here, that we see these behaviors at low values of the IMF. Well, that's when the minus grad P term is going to dominate, because J cross B is small. And everything is linear. There's no difference as a function of density, linear dependence on the magnetic field in the IMF. But when I get into the saturation conditions and the potential stops increasing the way it was increasing down here, now you see that there's a difference in the density. Higher density has got higher potential, just as predicted by those pictures. And we can actually see this happening if we look at the streamlines here for -5 nanotesla. All these streamlines connect, these first four, but go to 20 nanotesla. This streamline that was reaching the magnetopause now is going around it. And the geoeffective length is now only like this big instead of being much bigger. And for higher density, we see that actually what's happening is that you need a higher IMF to have the J cross B force dominate, because the J cross B force will dominate when beta is less than 1. Beta is the ratio of magnetic energy to plasma energy. So if the plasma energy is bigger than magnetic energy, beta bigger than 1, then minus grad P is the biggest force. But for a low beta plasma, that means that B squared over 2 mu naught is bigger than P, bigger than the pressure, the plasma pressure. Then the magnetic forces dominate. And so this beta less than 1 is really the signal of when you're approaching saturation, when you start to see these saturation effects. And I'm going to skip talking about conductivity. And this whole idea of saturation started with southward IMF, but you see it in northward IMF, both in data and in simulations. You see it for large BY, both in data and simulations. And in all of these cases, the transition occurs when beta starts to be less than 1. So really, we have what's called the modified Axford conjecture. So the overall merging rate between the solar wind flux and the day-side magnetosphere is determined by the forces on the magnetosheet flow, and this explains the relationship between solar wind conditions and the transpolar potential. Now, there was an argument a few years back about whether global or local control of the merging rate was more important. And Borofsky et al. Applied the Kashik-Shea formula for reconnection and said, well, if I've got extra density, it's going to slow the reconnection rate. And they did a simulation where they put a plume, like a plasmaspheric plume of density, and when it hit the magnetopause, sure enough, the reconnection rate in the plume dropped. But if you actually just integrate the total reconnection rate, they're identical. I mean, these are their own simulations. The gray area is the same for both. So what happened? Well, yes, the plume came and depressed reconnection right at the nose. Fine. But that meant that flux couldn't merge and it was pushed to the neighboring local time. And you see here that the reconnection rate went up. So even though it was depressed in one spot, it was increased in others, so the total area was the same. So global trumps local. And since this, there have been other studies showing the same thing, both simulations and observations, that the global control is the major factor in determining the overall level of solar wind magnetosphere coupling. So to conclude, the reconnection part of the transpolar potential for all values of IMFBZ can be understood using simple basic physics. So MHD, Faraday's law. So models that had to have some kind of special thing to account for saturation, they're not necessary because you can understand the entire variation from basic physics. Because from that, you can figure out what is the geoeffective length, why is the potential linear for small IMF, how does it transition to the saturated potential, and how do these quantities like the potential depend on solar wind and ionospheric values. And again, I skipped over the ionosphere, but it makes a big difference as well. As I said, I could spend hours and hours going through, this is a very high level view. For any one of these slides, I could have 4, 5, 6 other slides. And so that's another 5 or 6 hours. But the overall rate at which the solar wind flux is merged on the day side, it's determined by these forces on the magnetosheath flow. And those forces are established by the solar wind and the ionospheric conditions. So, and then my last point again, storms and substorms only occur for southward IMF because you need return flow up the tail to trigger reconnection in the tail. For northward IMF, you don't have any flow up the tail. You have flow down the flanks, and that actually weakens the viscous interaction. And for BY, you have flow, BY reconnection, you have flow across the tail from dawn to dusk, dusk to dawn. But that doesn't trigger reconnection because it doesn't compress the plasma by moving it towards the Earth and require reconnection to release the stress. So that is everything I've got. And I'd be happy to answer any questions. Let's see. I don't see any questions in the chat, but go ahead. Hola, Trinidad. ¿Cómo estás? Ok, pregunta si Sí, el substorm contribuye a la ring current, pero no tanto. No tanto. Durante tormentas, tú tienes más de los bursty bulk flows que entran llevando partículas cargadas para el interior de la magnetosfera. Y eso es lo que hace el ring current. Los substorms son parte de ese proceso, pero no son tan fuertes que pueden hacer un ring current grande. Y gracias por los saludos a Argentina. Yo quiero visitar, yo no sé cuándo, pero quiero visitar otra vez. ¿Quién más?
Bueno,
Também as perguntas podem ser em português, eu falo os dois.
well, thank you for the talk, but we have two questions, actually. One question is, does reconnection dominate just after the bow shock, while while in the magnetotail, the dominant process is viscous interaction?
No, no. The dominant process for solar wind magnetosphere interaction in general for the Earth is reconnection. Viscous interaction plays a role, but it is not a huge role. And the viscous interaction cannot create a storm or a substorm because it does not involve adding additional flux to the tail. There's no reconnection to add flux. It just creates some flows, and those flows are pretty much along the boundary. So viscous interaction, it does contribute to ionospheric currents, ionospheric heating, maybe a bit to space weather, but it will not create storms or substorms. And the amount of energy and momentum transferred by the viscous interaction is relatively small compared to reconnection, which dominates the flow of energy and momentum to the magnetosphere. And then to get a lot of activity in the magnetotail, and especially storms and substorms and the reconnection in the tail that produces the flows that go to the Earth, that carry particles, that are accelerated to make the ring current, all of these things, that requires southward IMF. Now, if you go out to Jupiter or Saturn, in Jupiter, the major source of energy for Jupiter's magnetosphere is Jupiter's rotation. By far, that's the major source of magnetospheric energy for Jupiter. It's internal. But if you go to Saturn or others, or even at Jupiter, I mean, even though it's dominated by internal processes, the energy that comes from the solar wind is dominated by the viscous interaction, not by reconnection.
Okay, thank you for the answer. But we have another question. If there is a time scale or a time average of the entire process from the moment that energy enters the system until it reaches the ionosphere through this mechanism?
That's an interesting question about the time scales, because actually I've got I've had students in the past that have done some work on this, and we never really sort of nailed it down. But I am working with one student actually at IMPE in San Jose dos Campos in Brazil on this very question of if we have a nice clean solar wind, so IMF is northward, and then suddenly turns southward. So it's like an experiment, right? Like a square wave. After it turns southward, when do we start to see activity in the magnetotail, and when do we get a substorm? And how does that depend on the solar wind parameters, like maybe the solar wind velocity, how big the magnetic field is, all of these things. So we're actually looking into that right now. But typically it's, half an hour to an hour kind of timescales before you start to see a lot of activity. Now, when the IMF goes southward, you start to see stuff in the ionosphere within just a couple of minutes, but it takes time to build up to, because there's induction in the system. So you have like an LC circuit, right? It takes time for the currents to build up and for that energy transfer to really reach its maximum level. So yeah, there's a part of the system that responds 20 or 30 minutes that's directly driven by the solar wind. And then the substorm activity, that is more like an hour-long time scale. But again, the details of that time scale and how it depends on solar wind activity, that is not entirely clear. And like I said, there's a student at IMPE who's actually under the direction of Alison Del Lago there, but I'm working with both of them, and we're looking into that particular question.
Thank you. And maybe the last question. What do you think about reconnection driving plasma flows and energy conversion? About the prediction of this one, of the reconnection driven plasma flows and the energy conversion, and what are the current challenges in the modeling these processes?
Okay, so if you talk about prediction, all right, the question is, do we understand all of the physics? The answer is no. We understand, though, maybe 90% of the physics of reconnection at Earth. We think we have a pretty good handle, especially with the results coming from MMS. Now, can we put all of that into a physics-based computer model? No, not yet. Maybe at some point we'll get there, but like MHD codes, they'll do reconnection, but it's completely numerical. It's not physical. And then if you try to put in, like if you do Hall MHD, and then you can get the right reconnection rate, that's computationally challenging. It takes a lot of horsepower to run such a code. And then as far as for space weather prediction, one of the biggest challenges is, do we have the right solar wind? Because we take the solar wind from L1 and we propagate it to Earth, but actually a lot of times the solar wind at Earth is not what Omni says it is, because the propagation isn't always great, or maybe the solar wind has got a bunch of different flux tubes, and maybe Omni's in one flux tube, but the Earth is in this flux tube just a little bit over, and so they see different solar wind. So for prediction, having the right input is really important. So we have many questions about that. The models, they continue to improve, but resolution and how much physics we can put in them, those are ongoing issues. And then the basic physics of reconnection we're pretty good on. So does that answer the question?
Yes, question. And the challenge also.
Yeah, lots of challenges. And in fact, last week was Space Weather Workshop in Boulder, Colorado. And people were talking about a lot of these challenges, because we can run our most sophisticated models, and we're still getting, at times reasonable predictions, at other times really terrible predictions.
Okay. Yeah. I think we finish everything. We thank you again for all this for all the explanation. It was very didactic, to be honest. And yes, if someone else has a question on the room, nothing. So okay.
And
So
you can always send me an email. Pueden enviar un correo electrónico. Pueden mandar un email.
yes. So thank you so much again. We see you in the next talk in the conference.
Yeah, the next collage, which is going to be in we're in Peru. What's the name of the place again? It's the
Arequipa.
very nice. Where?
Arequipa. Arequipa.
Arequipa.
Yes, it's going to be.
Yes.
Yeah.
With lots of nice ruins to go visit nearby.
Yes, for sure. And we are waiting for your visit. to eat a lot of food, Peruvian food.